the ultraviolet spectrum. Now, apart from giving you that sunburn or tan you didn't want, or tans, I think I'm like 5 different shades of white at this point from living in AZ my whole life. It's a fun time. But studying the universe in the UV allows us to learn quite a bit about the way that it works. For example, ultraviolet images of galaxies reveal key molecular dynamics behind the structure of stars and their evolution. Now, although we can gain an incredible amount of insight from studying the UV spectrum, developing instruments to examine it can be quite challenging. So, if you're curious about how UV optics work and what goes into their design, then I hope you enjoy this interview. Welcome, fellow space enthusiasts, to the very first episode of The Art of Space Engineering, the podcast which aims to explore the details behind how spacecraft and various payloads come together before launch and the lessons learned along the way. I'm your host, Sarah Rogers, and in today's episode, I had the chance to sit down with astrophysicist Dr. Paul Scowan to discuss his work in UV optical systems. Dr. Scowen is a research professor at Arizona State University's School of Earth and Space Exploration, where his work is centered around star and planet formation in massive stellar environments, as well as optical engineering for instruments operating in the UV spectrum. Now, in addition to his current work at ASU, he has also worked very closely with the Hubble Space Telescope. So if you're familiar with the photographs of the Eagle Nebula, also known as the Pillars of Creation, he is actually a co-author of those images and the papers associated with them. So ultimately, he has had an awesome career within the space industry and has stories upon stories to share from his experiences. So I've known Dr. Scowen since I came to ASU and started working on the Phoenix Cubesat. He's been a really great mentor to us over the years, so I'm so excited to have him as my first guest on the show. So in this interview, we will discuss the design of UV optical systems and how these are also driven by spacecraft interfaces, how these instruments are tested and calibrated, and the challenges that are faced in capturing high-quality science measurements. And we'll end up answering those questions by looking at 2 different projects which he's working on. The first is the Habitable Exoplanet Observatory, or HABEX. Now, this is a concept for a large space telescope which aims to directly image Earth-like exoplanets and characterize their atmospheric content. A UV spectrograph is just one of the instruments that HABEX incorporates to study the universe through a near-infrared telescope. The second mission is a 6U CubeSat, or a spacecraft the size of a shoebox, called SPARCS, which intends to use a UV camera to better understand how UV radiation might affect the habitability of exoplanets which are orbiting these low-mass stars. In fact, the mission is currently being led by faculty here at ASU, and the payload integration will be done at the university as well. On that note, I am so excited to have an outlet to share this information with you all, and I hope that you find this podcast equally as entertaining and informative as I have while making it. So without further ado, let's explore the world of UV. Welcome. Thank you for taking a risk on recording this podcast with me. So you have a really incredible background in the realm of astrophysics and astronomy. And so I wanted to start the interview by getting to know a little bit more about your career path. So what inspired you to pursue more of the science side of the space industry in the first place?
Well, I am by training an astrophysicist. That was what I got my PhD in. And the path towards that end started when I was probably 13 years old, when I was in physics class in what is called secondary school in the UK, high school here. And it was clear that my physics teacher came to the realization pretty quickly that I wasn't being terribly challenged in the physics class. And so I was getting into all kinds of trouble and mischief and stuff. So he encouraged me to get involved in a local astronomy club. And I grew up in southeast London. And so I got involved with these guys. And it was very helpful because being so close to London, when they met every month, they always had a lecturer come down from one of the colleges in the University of London to give various presentations, and it was very, very inspiring in a lot of regards. So when it came to that ultimate fork in the road at the end of high school, where you have to decide what you're going to do with yourself after school, it made perfect sense to me to go and study astrophysics, which is what I did at the University of Birmingham in the UK. And that was a great time, and I learned a lot. There was interface with some of the faculty who were there, who were at the time helping build parts of the ROSAT X-ray mission that was being built by the Germans, but the British were involved as collaborators. So I got to see a little bit, looking over the shoulder of folks, how missions were being defined and designed and built and things, even at that early stage. After completing my undergraduate degree, at that particular time, economically in the UK was not a particularly good place to be in terms of career opportunities. So I decided to go to the United States and completed my master's in astronomy and my PhD in astrophysics at Rice University in Houston, Texas. And that was a very educational, no pun intended, but a very educational period, because I got to learn a lot more about theoretical astrophysics. I got to learn a lot more about observational astronomy. And a lot of the computational tools, even at that point, which was in the late 80s, early 90s, that were available. This was just as the era of the World Wide Web was starting to come out, you know, from folks in Europe and folks from Illinois. And as I then graduated from grad school at that point, my first job was being hired onto the investigation definition team for the Wide Field Planetary Camera 2, the replacement camera for the Hubble Space Telescope, because of course the Hubble had been launched in 1990, and unfortunately, instead of being the resounding success that everybody had hoped it would be, because this was immediately in the wake of the Challenger disaster in 1986, it was not. The mirror was found to be the wrong shape, and so there was an awful lot of hand-wringing and embarrassment on the part of NASA, and so they engaged then in a very accelerated program to produce replacement instruments that had the corrective optics necessary to fix the aberration in the mirror, or the beam from the mirror. And that was my first job out of graduate school, was being part of that endeavor. And that was a very formative time in my experience. I got to do a lot of very, very interesting astronomy work with what was and remains in many regards the best instrument we've ever put together, the best observatory that's ever been flown to look at the universe around us. But it became clear after about 10 years of working with Hubble that some of the things that I was going to need to be able to do to advance my science were not available, were not even on anybody's planning charts. And so it became apparent that I was going to have to roll up my sleeves and get involved in the engineering and the instrument design side of things in a very real way. And since the early 2000s, that has been an awfully large part of what I do now, trying to look at the design options that are on the table, the kinds of technologies that are emerging, to try and build instruments or observatories that can enable different kinds of science. Now, a lot of this becomes fishing expedition work, right? You have to go through a lot of what are called concept studies to understand how these technologies may be brought to bear for the kinds of science that you're interested in. And you have to do this work well in advance of any announcement of opportunity that NASA might roll out. There's an element of tea leaf reading that comes along with it, where you try to anticipate needs based on long-term strategic documents that the various funding agencies put out. But you already have to have that mission concept pretty much figured out, designed, cost estimated, volume, mass, all of that stuff figured out before they even roll these things out. And so I have, in the intervening, 15 years now, done an awful lot of work that hasn't amounted to much in terms of real hardware that has actually flown. But it has influenced other projects that did fly And so that's been helpful, that's been useful. That has allowed us to define what the future of the kinds of astrophysics we want to do could look like. And it has shaped the developments of projects like WFIRST came out of one of the approaches that I had been part of, and other designs that, things like ultraviolet spectrographs have ended up in the HABEX large mission concept, and the idea of how to do ultraviolet imaging in a much more compact and modest form factor like we have been adopting with the Cubesat Sparks. So that was the short answer to your question, Sarah, is I wish I could have told you that I had a master plan back in the day. That wasn't the way it worked. It was something of a random walk that was influenced by the way things were going at any particular point along that path. But I ended up where I am today, partly from necessity, partly from interest, but partly from opportunity and luck as well.
That's awesome. I've known you for what, like 5 years now, and I've never actually had the chance to ask about this. So what drew you to the UV spectrum specifically, or is it just that much of your current work focuses on the UV and you've focused in other wavelengths as well?
Well, no. A lot of the work that I did as a graduate student, and then ultimately with the Hubble using the WIFPIC-2 after that, was primarily rooted in the optical, in the visible bands. So that's from like 350 nanometers up to about a micron in wavelength. A lot of the science that you do in that area is defined by gas ionization transitions, recombination transitions, which allow you to, in the case of what I was studying, which was the conditions under which stars form, and then once those stars form, how do they influence the environment around them for the formation of second or even third generation stars, and potentially the planetary systems that might form around them. So a lot of the diagnostics that I was using at that time were these recombination lines, which were primarily in the optical. Now, it became apparent to me, I have served on a number of different NASA advisory committees. And while I was the chair of what was called the Cosmic Origins Program Analysis Group, it became apparent that there was a need for better definition about what the ultraviolet could do for us in the immediate future. Now, this wasn't like ultraviolet suddenly came out of the woodwork. Ultraviolet astronomy has been around since the 60s. There were missions and rockets that were flown even back then that were taking advantage of the fact that the ultraviolet is a relatively high energy diagnostic that you would use to look at the environments around stars, or to look at the distribution of matter and energy in the interstellar medium. But it's a very challenging passband to work in for a variety of reasons. First of all, ultraviolet light is very easily absorbed or scattered. This is a logical extension of the Physics 101 explanation that they give you about why the sky is blue, right? The reason the sky is blue is that sunlight scatters most efficiently in the blue. And that is fundamentally the problem in the ultraviolet. It's very, very challenging to look at ultraviolet sources that are more than a certain distance away from us in our galaxy, because all of the intervening crud, the gas and dust and whatever, has a horrible habit of either absorbing or scattering that light out of our line of sight. So it's very, very difficult to actually do it. The other thing that also stems directly from that same physical process is that the construction and operation of ultraviolet instruments is very, very prone to problems with contamination. So if you are building an instrument and you've got all kinds of stuff, either dirt or grease that's gotten into the instrument, or the electronics boards, once they heat up, start to outgas volatile material, particulates and volatiles can get in the way and absorb those ultraviolet photons before they ever get to the back end of your instrument, to the detector that's going to record the photons. And so you have to go through this process of building the instrument in an extremely clean environment. And that is very challenging in a lot of regards. So when you're building or designing ultraviolet observatories, you have to be very, very disciplined about the environment that you build them in and the way that you're intending to use them in space, because once you're up there, space for the most part is relatively clean, but if you're in low Earth orbit, for instance, there is a high tail to the Earth's atmosphere of atomic oxygen, and that can serve as a contaminant as well. So you have to worry about that and build mechanisms into your instrument or observatory that allow you to decontaminate the system periodically because of buildup of this kind of crud. So that's a lot of the challenges behind it. But what you get from going to the ultraviolet is access to a whole series of different resonance lines. In fact, there's a chart that I use in some of my proposals that shows the sheer number of diagnostic lines. So these are spectral lines, either in absorption or emission, that give you direct access to things like electron density, electron temperature, dynamics in terms of the width of the line. And this kind of information is not available in a lot of other parts of the passband, either the visible or the near infrared. And because it represents very energetic states, it actually represents an awfully large part of the energy budget when you're trying to look at the balance and distribution of energy and matter around hot sources like massive stars, or the interaction of gas clouds with each other and things like that. So the ultraviolet provides you that kind of opportunity, but it comes at a price, and that price is the difficulty or complexity of your system that you might choose to build to access it.
Right. I think that's actually a pretty great lead into the next topic. So to give our listeners a little bit more of a background on today's main subject and segue into more of the meat of the episode, how does a UV spectrometer work exactly?
Well, a UV spectrometer is, for the most part, like a regular spectrograph. So you have a spectrograph needs to get its light from somewhere, so you usually bolt it onto the back end of a telescope, right? So a telescope is essentially a light bucket. It is a large collecting surface that is curved, and it will collect as much light as it can get its hands on and bring it to a focus, because the mirror itself is concave. And what you try to do is that as that light comes together to a focus, so the beam is converging, you then take that light. Usually you use some kind of an aperture stop so that you're selecting what part of the field of view of the telescope you're actually going to take the light from. This avoids confusion and light coming in from other sources that might get into your system and confuse the result. So you have some kind of a slit or aperture that is put close to the first focus, the primary focus of your telescope, and then the light diverges again once it goes through that aperture. And then you take that light and you pass it across or off the surface of a dispersive element. So this is, as a transmittive material, it could be a prism, just like the kind you use in college level physics lab, where you take the light from the source and you spread the light out using the dispersive powers of a prism, or you use a reflective grating, which is usually a metal surface with lines ruled into the surface. These are mechanical lines etched into the surface, and you can use the diffraction off of those lines to produce constructive interference in a particular angle or direction coming off that surface, and that allows you to disperse the light as well. So this is just a conventional dispersion relation that is exactly the same optics that controls, how light diffracts going through a small aperture, a pinhole, if you like, to produce an interference pattern on a screen that you might put behind that pinhole. So in the ultraviolet, there's not many transmissive materials that actually will allow you to pass ultraviolet through without huge losses. So all of the ultraviolet spectrographs that are really in design or in actual operation are reflective systems. Every single surface is a reflection. So you take that light coming through the entrance aperture of the spectrograph, you bounce it off this dispersive element, this grating, which is usually about 4 or 5 inches in diameter. Is round, has these rules, these metal grooves etched into the surface at a rate of something like 300 grooves per inch or so. And that light is then dispersed at a particular resolution, and we characterize the resolution of a spectrograph by this thing called the R factor. And the R factor is, at any given point in the spectrum, the wavelength of light at that particular point divided by the smallest resolution element that you can resolve in the spectrum. So it's lambda over delta lambda. And, you know, so low resolution systems have an R of a few hundred. High resolution systems have tens of thousands of resolution elements at a particular wavelength. But that light is coming off that reflective surface, that dispersive surface, still in a diverging beam, and you need to bring it to a focus. So there is usually a collimating mirror that takes that light and then brings it to a focus, and that's where you put the detector to record the spectrum. And the idea is that, just like any spectrum you've seen elsewhere, that wavelength maps to a different physical location on that detector in a particular linear arrangement. And then that allows you to then map directly the change in brightness of the light that you're getting from your source as a function of wavelength. And that's really what a spectrograph is. An ultraviolet spectrograph, in terms of the things that make it different, I've already mentioned that it has to be all reflective because transmissive doesn't really work. You also need to design it with as few reflections as possible. The problem in the ultraviolet is that the efficiency of the reflective coatings that you might put on these mirrors, first the telescope mirrors, the reflectivity of that grating surface, and the collimating mirror, they're all not very good. They're like, best case, 60 to 75% reflectivity. And so you can imagine that if in a typical design you've got a telescope, so it's a primary mirror, secondary mirror, diffraction grating, and the collimating mirror, that's 4 reflections already. So you take 75% and raise it to the 4th power, and you start running out of photons in a hurry. And this is already, remember, in a pass band where the universe has conspired to try and scatter or pre-absorb the photons you're trying to observe in the first place before they ever get to the telescope. So you try to minimize the number of reflections, and then the detectors that you would use, there's a new set of new generation ultraviolet sensitive CCDs that have been produced by places like JPL and a few other companies. These are relatively new, but they're showing a lot of promise. But a conventional device that is far more experienced, has much higher heritage, are these things called microchannel plates, which are a form of cascade accelerating detector. So a photon comes in the front end of one of these things. It hits a material on a piece of glass that has a series of holes bored through it. These are tubes, they're not just holes. And on the surface of the interior surface of those tubes is a low work function material. So as the photon comes in, it hits that material and liberates a bunch of electrons that get thrown literally off the surface out into into the volume of the tube in the glass, and you put a voltage across that plate so that the electrons are accelerated away from the incoming surface. And then ultimately you have a detector on the back end of that glass plate where the tubes empty out, if you like, and that's where you record the pulse of electrons that came from that photon hitting the top end of the plate. The differences between those two is the microchannel plates, because of the way the electronics are wired, they allow you to count individual photons, because a single photon liberates in the end millions of electrons that produces a very easy to measure pulse. So you can literally measure each photon as it comes in. So MCPs, or microchannel plates, are generally referred to as being photon counting devices. They also operate at room temperature, which is a great thing thermally, because CCDs have to be operated very cold to keep their read noise and dark noise down. The problem when you have a very cold surface in an ultraviolet instrument is that any volatiles that are floating around are going to stick to the cold surface. It becomes the preferential place for stuff to get stuck. But that's exactly what you don't want in the ultraviolet, right? If you start collecting the volatiles, the very things that are going to absorb the signal that you're trying to measure, then you are contaminating your detector because you're operating it cold. And so that drives another layer, another level, if you like, of contamination control that you have to achieve to stop your detector from getting crudded up. So these are the kinds of challenges that you don't oftentimes have to worry about too much in the optical or the infrared. But in terms of the operation of a spectrograph, it's very, very similar in most regards, but there are concerns like the ones I just described that complicate the use of it.
What is the output that you actually get from the instruments, and then how is that used during post-processing to allow you to actually perform scientific analysis?
Okay. For a CCD, from one of these ultraviolet CCDs, you get an image, right? Just like a digital camera, you get a picture, and the picture you get is a picture of the spectrum. So it's a series of emission lines, if you're looking at gas, for instance, or if you're looking at a star, it's the bright stellar continuum. So it's a continuous spread of colors with lines, with black lines missing in the spectrum that have come from the absorption of that particular wavelength by stuff that's either in the photosphere or the chromosphere of the star. In terms of a microchannel plate detector, what you actually get is a stream of data that comes out the back end that is essentially the XY location of where that photon hit on your detector and the time at which it happened. And then you have to build your image after the fact, right? You take this stream of numbers and you build a two-dimensional image using that XY data, and then the intensity, of course, as well as the time. And you take the intensity from that photon pulse, and then you build up your image from the beginning of the stream to the end of the stream during the observation to produce the same spectrum that I just described for the CCD. Then what you have at that point is a map. You have a spectrum that is in one direction, it's spatial. That's the narrow end of the spectrum. The broad end of the spectrum is then the different wavelengths mapped to different X locations along the spectrum. And that allows you to figure out, once you've calibrated the spectrum, that, okay, this line that we're seeing at X position 234 in the spectrum is actually the emission at a particular wavelength of 107 nanometers, for instance. So that allows you to calibrate what the wavelength of each of the lines that you're seeing in the spectrum is. You can then use calibration sources to figure out what the intensity mapping is, because all you're going to get out of your data is a number, right? It's going to be the number of electrons or the number of photons that it collected. but you don't know exactly what that means in terms of the calibrated flux coming into the telescope at the front end of your observatory. And you have to use calibration sources to figure out the mapping between that number, that data number that's recorded in your spectrum, and what it means in terms of actual photon flux hitting the observatory at the front end of the system. And then you can look at the structure in those lines, the separation of them, how wide the lines are. All of that kind of information starts to give you the kind of information I was talking about much earlier on, things like the density of the electrons of the gas that emitted the light in the first place, the temperature of the gas that emitted the light in the first place, the spread, the width of the line tells you how fast the material was moving that emitted that light or absorbed that light in the first place. There's all kinds of astrophysical quantities that you can back out just from analyzing the position, shape, and distribution of light in each of those emission lines. That's why spectroscopy is as powerful as it is. It's not just a picture. You're looking at all kinds of astrophysical information that is encoded into the lines in the spectrum that you see.
That is literally so cool. That's so cool. This is the kind of stuff that got me just really inspired and interested in space in the first place. So I love that.
Wonderful.
All right. So I saw that right now you're working on a few missions which are very different from one another. One being Sparks,
Yes.
which is a CubeSat the size of shoebox, and the other being HABEX, which is a very large space telescope. So in
Right.
both cases, you're dealing with very different volume constraints that you have to design your optics around. I recall from the UV spectrograph section of the HABEX concept paper that you guys ran into some optical design challenges due to volume constraints you had. So what I was wondering is, how exactly do volume constraints constrain, or do volume requirements constrain the optical design? And then how is that different between like Sparks and HABEX?
Okay, yeah, you're absolutely right. Volume constraints, or packaging, as it's called in the business, is a very challenging part of this, right? You know, the optical designers can sit there in their wonderfully well-controlled world and come up with a fantastically efficient optical design that does everything that your science traceability matrix needs, that the mission needs to achieve in terms of resolution, in terms of throughput, all of those things that you care about. But most times, right out of the box, it's not packageable. The mirrors have to be fit into a particular space that's available. And now a lot of the times this space is defined by the launch vehicle that you're trying to package this thing into so it can get into space. I was involved in a proposal, or an attempted proposal, for a small explorer last year. And in the end, we couldn't make the proposal in that particular case because the project, or the instrument they came up with, was too complicated to be buildable within the cost cap. But one of the challenges that we were having to wrestle with in that particular case was that small explorers are very modest in terms of size and cost. And the preferred launch vehicle is the Pegasus, which looks for all the world like an intercontinental ballistic missile and is launched from the underside of an L-1011. And when you look at the available space in the Pegasus launch vehicle, it's very, very tight. It has a very limited length of only 2.12 meters. And if you're building a spectrograph, there's an awful lot of optical beam that you're having to package in there. That whole process I described, going from the telescope through the entrance aperture, off the dispersive element, off the collimating beam, and to the detector, there's beams flying left and right, and trying to make those things fit into this very modest space is very, very challenging indeed. Now, in the two particular projects that you've asked me about, HABEX is it's a 4-meter entrance aperture, a 4-meter primary mirror telescope with an off-axis secondary. That means that the light comes in off of the mirror, and the mirror is tilted slightly so that the light goes off to the one side and then hits the secondary mirror, the relay mirror, actually outside of the incoming beam, so that there is no obscuration. There's nothing getting in the way of the light coming into the telescope. That design choice was driven by the primary science goals of HabEx, which is the ability to take the light coming into the telescope and then pass it into a device called a coronagraph. And a coronagraph uses a series of interesting Fourier optics sleights of hand to extricate the primary light coming from the star itself and throw it away, so that all you're left with is the light coming from sources very near to that star. In other words, planets that are orbiting that star, and you're looking for the reflected light from them. Now, this places very, very stringent control requirements on the wavefront, on the light coming off of that primary mirror, and how it is handled after that. In the case of HabEx, the general astrophysics instruments, and there's a wide field camera, and there's this ultraviolet spectrograph that I was the science lead for. That light has to be picked off then off of that beam coming off the secondary mirror and fed into your instrument. Because of the way we were doing this to keep the light as clean as possible, it meant that there were very stringent requirements about where you could put stuff around the telescope, on the walls of the tube of the telescope and back behind where the primary mirror was. And we didn't want a hole in the primary mirror, because a lot of telescopes do that, right? They bounce the light off the secondary and take it through a hole in the center of the mirror. They didn't want that. They wanted as clean a reflected wavefront as possible. So it meant that our ultraviolet spectrograph and all of the beams that we had to handle had to be packaged down the side of the observatory and then back behind the primary mirror using a fold mirror. You remember what I said earlier, that in the ultraviolet you want to minimize the number of reflections that you use? Well, this challenge of trying to fit the instrument into a particular place around the telescope tube itself forced us into a place where the number of reflections involved in the entire instrument got as high as 7 or 8, and that's very high. The one saving grace that we have is that this is behind a 4-meter mirror. So it has a lot of collecting area and can make up for some of those losses. But it was definitely true that the design we ended up with in the end for the large mission concept study that was named HabEx was not, in many of our opinions, the optimized, the most efficient design that we could have come up with. But it was the one that we ended up with in the limited amount of time that we had to perform the study. So that was the challenge in that regard. Now, when you turn your attention to a Cubesat, the problem with a Cubesat is that every millimeter of space counts. Everything is made a lot smaller. It is packed together very closely. And so in the case of our optical system for that, now remember, this wasn't a spectrograph, this was an imager. So it's basically a telephoto lens, that's the telescope, with a detector or 2 detectors on the back end. And in that regard, we had a very modest, very compact telescope. It was only 90 millimeters diameter entrance aperture. But the telescope itself was only about 11 centimeters long. And the beam comes through in that particular case, it does have a hole in the mirror, comes through the hole in the mirror. We put a dichroic in it, which is a reflective piece of glass that has coatings put on the surface. that work as an interference cavity. It's essentially a Fabry-Perot echelon, and it allows you to bounce all of the light shortward of a particular wavelength. It reflects off the surface of that piece of glass, which is usually held at 45 degrees. And then everything that is longward of that same particular wavelength is then transmitted through the dichroic and goes to another focal plane behind it. So the use of a dichroic allows you to split a single beam from a telescope into two focal beams that then can serve or feed two separate detectors. And that was how that's how we're doing Sparks, is to have a far ultraviolet and a near ultraviolet channel with separately optimized detectors, one that works better in the far ultraviolet and one that works better in the near ultraviolet. And that's how we're doing it. But the tolerance for how tight these things have to be put into the space in this CubeSat, we have to worry literally about every single millimeter of space that we use. And if something has to go longer, then there's weeks of debate and meetings about whether we can actually afford to give up that space because it's going to take space away from something else. So CubeSats are very, very challenging when it comes to packaging.
Right. Now, we encountered similar issues in terms of space on Phoenix as well. And granted, it didn't require a week long of meetings. We did pretty much max out the entire volume of the CubeSat, and it definitely became difficult to work with space later on. So kind of continuing off of that topic, one thing that I was really interested in learning more about was how the spacecraft side of things can be affected by incorporating a UV spectrometer. So to poke at one area in particular, target visibility and stability control, for example, are both really important for obtaining high resolution science. So how do the science needs translate into requirements for attitude control and determination?
Well, there's a whole series of things there, right? One of the things that when you're trying to point an observatory, which is just fundamentally a spacecraft, at a particular point in space, and you want to keep it pointing there so you can do an extended exposure or a variety of different exposures without having to keep moving the observatory around, one of the things you care about is where the center of mass of the system is, and that you want it to be all oriented around a particular place in the spacecraft that you can then put the reaction wheels or the thrusters or whatever it is that you're using to control the attitude of the spacecraft, that they don't have to work very hard to keep it where it's supposed to be. The bigger the spacecraft, the more inertia it has. So if you design it right, if you park a spacecraft looking in a particular direction, it pretty much will stay there until some outside force acts on it. Now, that outside force can be the upper edge of the Earth's atmosphere if you're working in low Earth orbit. It can be the influence or the impact of the solar wind if you're working out at Earth-Sun L2 or Earth-Sun L1. So you generally have to build systems into the spacecraft that can move it around and can adjust and correct things as you go. But understanding how that control works and what is driving the pointing stability, the natural tendency or the natural ability of the spacecraft to point in a particular direction is what we call body-centered pointing, and it really just comes from the inertia of the spacecraft as a whole. If you have to add additional attitude control on top of that, then sometimes it comes in the driving signal comes from a star tracker, and usually you have more than one of these that looks at a fixed point of light in the sky, another star, usually not the one you're looking at with your science instruments, and keeps it in a very particular place on the imaging camera that is attached to that star tracker. And what it does is it just keeps taking a picture every second or every fraction of a second to make sure that star's where it's supposed to be. As soon as that star starts to move off of where it's supposed to stay, then the attitude control system figures out which direction the spacecraft is moving and then either uses reaction wheels or magnetotorquers or simple chemical mechanical thrusters to move the spacecraft back to where it's supposed to be. One interesting fact about the HABEX design is that because the pointing stringency for the coronagraphic measurements was so high, we couldn't even use reaction wheels in the design of HABEX. The motion, the flicker, the jitter that comes from spinning these things up, reaction wheels are little flywheels. There's usually 3 of them oriented perpendicular to each other. And the idea is that if you spin a flywheel up in one direction, because of the conservation of angular momentum, the spacecraft will rotate the other direction. So you can use 3 reaction wheels oriented perpendicularly to each other to control all 3 axes of motion of a spacecraft without using thrusters. However, the problem is that when you spin that wheel up, it introduces a rumble, a jitter to the spacecraft, and the whole thing vibrates a bit. And that rumble, even from the best reaction wheels we could find, was still too much for the requirements, for the specifications that the coronagraph needed to keep the signal as clean as possible. So in the end, the design choice that was made for HABEX, and this is pretty revolutionary, is to use nothing but microthrusters, using solid iodine and a variety of other thruster fuels to keep the spacecraft where it's supposed to be. There's no reaction wheels at all. And this was a bit of an eyebrow raiser when we first ran into the problem. But in the end, the people who were doing the design work proved to the doubters, i.e. the scientists, that it in fact could do the job that it needed to do, and it was a relatively low risk solution. So this was something that was quite remarkable. Now, in the case of a Cubesat, you don't usually have room, going back to our earlier discussion about limited space, you usually don't have room for a thruster system. So all of the attitude control in most Cubesats in low Earth orbit are achieved by reaction wheels and magnetotorquers. Magnetotorquers, just to mention, to be complete there, magnetotorquers use the magnetic field of the Earth to exert a force on a spacecraft. The idea is that you pass a current through a magnetotorquer, and when you cross a current through a magnetic field, so as you orbit the Earth and you're going through the magnetic field of the Earth, that gives you a force, a magnetically induced cross-product force that you can use in exactly the same way as a reaction wheel to control the motion or the speed of the spacecraft in a particular direction. So again, you have 3 magnetotorquers arranged perpendicularly to each other, and you control the current through them to control the rate at which the spacecraft slows or turns as a result.
Yeah. And what you brought up there about only using microthrusters for HABEX is really incredible. I think it just really goes to drive home just how absolutely significant stability control is, given that your science relies upon having these long exposure times to what you're looking at. But apart from attitude control and how it probably kills the souls of the engineers working on it, are there any other challenges that are faced when designing the spacecraft to support UV spectrometers?
Well, what I've talked about so far is just pointing at a particular target. The choice of orbit that you end up in defines your field of regard, right? If you're in a sun-sink orbit running around the poles, you have an entire field of regard looking anti-sun that is half of the sky. And that is very helpful if you're bouncing around between lots of different targets, astronomical targets that you would like to take data of. But one of the things you've got to worry about when you do that kind of thing is where on the spacecraft you're going to put your solar panels if you're going to be using the sun as your energy source, because those panels have to be pointing at the sun. If you turn the spacecraft too much one way or the other, then you change the angle of incidence that the sunlight comes in on those solar panels and the amount of power that they generate. So if you have a spacecraft that turns a lot, those solar panels might have to be gimbaled. They can't be body mounted. They can't be bolted to the side of the spacecraft unless you put a solar panel on every single side of the spacecraft, which some people have opted to do. But that's one of the concerns. The other concern is thermal regulation. The sun is the biggest source of heat when you're up in space. You do generate some heat internally in the spacecraft, but that can be mitigated and thrown out through a radiator, usually on the side of the spacecraft. But again, if you're turning the spacecraft around a lot, and it depends on the orbit that you're in, you don't want that radiator pointed at either the sun or the Earth. You would like it to be pointing at deep space, because it will come into radiative equilibrium with space at something like 40 Kelvin. Unlike if the radiator points at the Earth, it'll come into radiative equilibrium at more like 300 Kelvin. Oftentimes it's got not a lot to do with the science you're trying to do, other than understanding where in space you have to point relative to your orbit. But these are all the kinds of concerns that you have to worry about. And it all becomes this trade, this balancing of requirements against cost and performance to make sure that the mission that you ultimately fly is capable of doing what you need it to do.
Right. So earlier you'd mentioned that decontamination was especially important for ensuring that you can absorb as many photons as possible. So how do you go about managing decontamination exactly?
Well, we borrow an awful lot of our practices from the semiconductor industry. The same kinds of full head-to-toe PPE that we are now, as a community, very used to in the last 3 to 4 months, understanding the utility of PPE and what it does for you. But what that allows you to do as a worker in a clean room, the PPE isn't so much about protecting you, as we are used to in the medical world. It is about keeping all of the stuff that comes off your body inside your suit, inside your gown, so that when you're in the process of working on an ultraviolet sensitive instrument, that the skin cells that come off your hands, the grease that's on your hands, the hair follicles that come out of your hair or your beard, perspiration, any of the skin oils, let's say, that can be put onto a surface if you do it wrong, that can completely screw up the instrument itself. So we have to develop very regimented protocols that we use in the clean room environment to make sure that we at no time come into contact with any sensitive surface, be that a reflective surface for the optical side or the detectors themselves, that might preferentially introduce materials that would either scatter that light away, that would be particulates, right, like skin and dust and things like that, or that would preferentially absorb the ultraviolets. That will be oils and volatiles and stuff like that. So it's a matter of being very careful about handling stuff, trying to operate and calibrate and put stuff together in a clean environment or even a vacuum environment. And then when you've got hardware that you are in the process of building that you know is relatively clean at this point, you have a number of tools available to you to keep it clean and to make it cleaner. To keep it clean, we have cabinets that we use that have a continuous flow of very clean, dry nitrogen gas. That's called a purge environment. So you put stuff into these cabinets that have a positive pressure, right? So that stuff can't get into them. It only blows the nitrogen out and keeps the equipment that's put in there very clean indeed. But we also have to go through processes like mechanical cleaning, which uses wipes and isopropyl alcohol, to clean surfaces. Some surfaces you can't clean because they're too delicate. Some of the optical surfaces that we use coatings to enhance or retain the ultraviolet reflectivity that you can't physically touch. And so those have to be cleaned in some regards by actually heating them up. I referred to some of these molecules as being volatiles. That's the deal. They, when they heat up, they de-adhere from a surface and will float around in the air as molecules. And you want to keep that stuff away. And so baking stuff out is another technique that we use to try and take stuff that is covered in volatiles and to boil that stuff away. And the bake out systems that we use often have a vacuum pump attached to them. So as the stuff is baked away, it is then sucked away by this vacuum pump. And you're left with a very clean system when it comes out of the oven. So these are some of the techniques that we choose to use. But the other thing we have to do is just monitor the level to which we are keeping things clean. And so we use things like witness plates, which are either glass or metal surfaces that go along with all of the hardware and experience the same environmental conditions as that. And as you go through, you go and measure these things periodically to see what kinds of particles or volatiles have adhered to those surfaces, and then you use them as proxies to therefore monitor and tell you how much contamination might have been deposited on the stuff you care about, the flight hardware that you're building. And if that's the case, then you go back and you have to go through another series of cleaning steps to try and get that stuff back into a state where you trust that it is clean enough to be able to fly into space and to do the job that you're building it to do.
And you also mentioned that you also have to build in mechanisms to control decontamination. So what do you do for that?
Of course, you realize that contamination is not something that you can prevent. It is something that you can budget. And so that's part of it, right? That monitoring that I was just talking about there, you're never going to achieve zero contamination. But if you can keep the contamination below a predefined level, then you know that the performance of your system will be adequate to the task you're designing it to do. Now, the problem is that while you're building it, you've got relatively good control over the environment that you're doing this in. But as soon as you go and bolt this thing into the fairing of a rocket, usually not in the cleanest of environments, they're relatively clean, but they're not the cleanest. And then they go roll it out onto a launch pad in a very moist environment, i.e. Florida. There's an extremely good chance that a bunch of volatile material like water and things like that could adhere to the kinds of surfaces that you care about in your instrument. And so what we tend to do with ultraviolet instrumentation is we build in heater circuits and things like that that allow us to do the same kind of bake out that I was talking about that we do here on the ground, but to do it in space. The vacuum is already provided for you by the environment that you're doing it in orbit. And the nice thing about that is that the vacuum, even in low Earth orbit, is far higher. It's far higher grade in terms of vacuum than we can ever pull here on the ground. And so the mean free path for a lot of the volatiles that we want to get off our various surfaces are far longer in those environments. They're measured in hundreds of kilometers. So once you get a volatile off a surface in an instrument through heating or whatever, and you've provided that molecule an exit path, a way to get out of the instrument, there's a pretty good chance you'll get it out and it'll never come back. So that's part of the approach that we tend to use. It's not something that you tend to go through this immediate scrub right after launch, and then you may have to periodically do it every few months, maybe. And it only takes, like a few tens of hours to do it. So you don't lose a lot of science time, but it is something that you have to do to keep the performance of the instrument where you need it to be.
That sounds exhausting. I'm sorry.
It's not as bad as it sounds. It's something that, if you're using calibration sources, either built into the instrument or you're using an external source, you can usually see when contamination starts to become an issue just simply because your signal flux starts to drop. But as long as you built in a mechanism, a strategy with which to remove the stuff, you're usually in pretty good shape. There is one threat, one sword of Damocles that you might have to worry about, especially when you're building a system that's to work in the ultraviolet, is that if you are pointing your instrument at a particularly bright ultraviolet source, like the sun, for instance, if you have volatiles on the surface of critical surfaces like optics and detectors, and you expose it to very intense ultraviolet, you can actually photopolymerize the volatiles into a form, into a state that you couldn't even get them off if you had a hammer and chisel. And so that's a major concern. For astrophysics, we tend to try and avoid pointing at the sun. We tend to try and point the other way, right? And look at the faint universe. But if, for instance, you're building an ultraviolet instrument that's supposed to do heliophysics, then this becomes a huge deal and something that you really have to be, in some regards, even more stringent than we have to be for astrophysics to try and at least keep the volatiles off the critical surfaces.
I mean, I knew Sparks had really strict contamination control requirements, but I didn't know exactly like what went into that. So that's really interesting. And it's
also band dependent, right? Because Sparks is not a spectrograph; it's an imager, right? It's essentially an imaging photometer, and it has two bands. It has a far ultraviolet and a near ultraviolet band. The bluer you go, the bigger a problem this is. So the near ultraviolet band, by comparison, is actually relatively insensitive to contamination. We've done worst case scenario modeling of how much crud can we actually put up with and how much impact will it have. And over the 2-year lifetime of the Sparks project, worst case, we have a baseline mission of 1 year with an extended baseline of 2 years. But even after 2 years, if we did no decontamination at all in space, we still would only be looking at a reduction in throughput that's probably less than 15%. The far ultraviolet is a very different story. We looked at this and found that if we did no decontamination, we would probably have lost more than 60% of our throughput within a matter of months after a contamination event. If there had been some outgassing or exposure to volatiles in space, that would have crudded things up. So it's very sensitive in that regard, and the bluer you go, the worse it is. So the contamination demands, the contamination requirements that we're maintaining for Sparks are all driven by the far ultraviolet channel and not the near ultraviolet.
okay. So the last major section that I wanted to focus on is more to do with integration and testing, or the fun part where nothing works and you have to make it so. So INT for optics in general just seems to be a very like meticulous process, and like with anything else with INT, I know that like it has to be done in a certain way so you can kind of test and validate as you go to make sure you resolve problems. So I was really curious as to like what the systems integration and test process actually looks like for UV spectrometers, for example.
Any optical system that you want to fly in space is mounted on what is called an optical bench. This is an extremely rigid backbone that the optics are mounted on, so that when you go through things like vibrational tests in pre-flight certification, or when you go through the process of operating this thing in space and you've got maybe a thermal gradient across the spacecraft that you really don't want to have, but sometimes you still have one, that the optical system as a whole is robust against those problems. That the mechanical stresses or the thermal stresses impart no variation in the relative position or tilt of the optics in the system so that it works the way it was designed to under a variety of conditions. Now, that's just making sure the thing keeps working, right? That the beams are still lining up, that you're delivering your image or your spectrum to the detector where you expect it to be. Over and above that, the other big thing that you have to worry about with AIT, with optics, is calibrating the system. Now, I touched on this a little earlier. Sometimes, when you're in the lab, you've got a variety of tools available to you, monochrometers that deliver a known flux as a function of wavelength into your system that allows you to map and calibrate what the overall throughput, the impact of all of those reflections or transmissions on the actual amount of light that makes it all the way through the system to your detector versus how much came in the front end. Mapping out that and understanding that, you can use a monochrometer, you can use devices like calibrated photodiodes to understand where the losses in the system are. You can measure the light before it hits a reflective surface, the light after it hits a reflective surface, and know exactly what the reflectivity of that surface is. And if it's not up to spec, if it is not what you ask the manufacturer to give you, then you send it back and you tell them to do it again. That's part of the acceptance testing approach. But ultimately, you have to make a decision about how you're going to calibrate this system once it is in space. You can calibrate the heck out of it while it's down here on the ground, and that information can be used to instruct the performance that you see in space, but it is never going to be the same. There's going to be something else that gets in the way, that there's contamination events, or that maybe things got slightly knocked out of whack, or that the telescope isn't performing quite the way it was supposed to under a particular set of thermal conditions. So you have to come up with a strategy for the calibration, and sometimes you use an external target, you use something else, a star or a source in space of known brightness. That's really what you want, right? Is a source that you know how bright it is. And when you look at that light and you record a particular signal, you can use that known number at the front end to back out what your calibration is on the back. And that will then immediately tell you if things are good or things are bad. Now, sometimes you don't have an external source that you can use in this way, and sometimes you have to build in an internal calibration source that is a lamp or a source of some kind or another that you know exactly how bright it is. And there are various companies that produce these calibration sources. But you have to have a flip mirror that flips in and takes the light from the lamp and puts it through your instrument instead of the light coming from your telescope or from the outside the spacecraft. And a lot of instruments I've worked on have done that. You do need to understand how that source varies with time, that sometimes those cal lamps will vary in their brightness over 6 months, a year, 2 years, 3 years, 4 years. That kind of information is usually measured and published by the manufacturer of the source that you choose to use, but it's something you need to roll into the calibration as well. So the challenges in the AIT are mechanical, optomechanical, making sure that the optics stay lined up and that you understand when they move and how they've moved and what that does to the throughput of the system. But it's also understanding and using tools like external or internal sources to actually directly measure the throughput of the system and what that tells you about how you need to use the system. It doesn't stop you from using the system to do your science. What it changes is what the numbers mean for your scientific measurements on the back end.
Okay. Are there any other special tests that you guys have to do in order to accommodate more of the spacecraft concept of operations and general design? For example, with Phil Christensen's instruments, we will do gravity compensation tests to make sure that if the spacecraft is in a different orientation, that doesn't affect the response of the instrument and the actual science that we're able to do. Is there anything like that?
Yeah, what you're describing there is called G release, because of course the problem is you build the optics down here on the ground. where you're under 1 g of gravity. And what you have to do when you're designing your optical bench is make sure that you're worrying about where that g vector is, because then once you put that same optical bench into space, it will not have that g. There will be a release of the g-force. And you want to make sure that you designed your optical system in such a way that that g release doesn't change the alignment, or it changes the alignment in such a small way that you don't care. An extension of this that is not related to space or spacecraft is the idea of building very high resolution instruments that go on telescopes here on the ground. And the telescopes move around as they look at the sky, right? And the G vector changes with the instrument as it does that. So in the same way, you worry about the same problem there, that you're not talking about G release, you're talking about G change, that the acceleration vector or the force vector changes direction, and that could change the alignment of your instrument. But this comes back to the rigidity and the design of that optical bench that I was talking about. And as long as you make sure that the interface between the telescope and the bench really is as rigid as it needs to be, without making the system so rigid that it will fly to pieces when you go through testing for vibration and stuff, then you can usually do a pretty good job of that. It is a concern, but it's one that if you design the optical bench correctly, it should not be a problem.
Okay. Okay. So last question that I want to ask for this interview is: do you have a favorite story from any of your past or current projects that you would like to share? It can be fun. It can be a story of terror.
There's a few, but one of the ones that was a tale of success in some regards was the work that we did on the WIFPIC-2. The WIFPIC-2, remember I told you that all of the instruments that have subsequently been flown and installed on Hubble had to contain their own corrective optics built into them. This was because, you know, an awful lot of the Hubble was designed to be replaced or repaired or upgraded on orbit, with the singular exception of the primary mirror, which was where the aberration problem was. There was no way to replace the mirror short of getting out a circular saw and cutting a hole in the side of the spacecraft. So what each of those instruments had to do was they had to put in a corrective optic that had exactly the same error, but with the opposite sign. And that optic had to be lined up with the optic axis of the telescope and the instrument to a very high degree of accuracy. The optic itself was, you know, only maybe an inch or two across, so it could fit inside the instrument. But when you actually did the analysis of how well that had to match the position of the optic axis, it was at the tolerance level of a few microns, which was extremely challenging. And remember, the way the instruments are installed on Hubble, a couple of burly astronauts go up there, pop the hood, pull the instrument out, put the new one in, and the instrument rides in on a set of rails, and there's a pick-off mirror that picks off the light from the telescope and feeds it into the instrument. The amount of play that was in those rails and the latches that hold the instrument in place was not at the micron level. So there was no way for us to guarantee that the beam coming into the instrument was going to be as well understood and well aligned as we knew it was going to need to be. So we had to come up with a technology that is now actually relatively commonplace, but back then in the late 80s, early 90s was entirely new technology. This was a thing called an actuated fold mirror. The idea that you had a mirror with the correction, the optical correction built into it, that was on the end of a mechanical arm that you could move around. So it was actuated. We do this a lot now with things like hexapods and stuff like that. It's very common for us to actuate optical surfaces. But back then it was not, especially not in space. So we had to come up with a whole new technology to do that so that we could move the mirror around once the instrument had been installed, so that we could make sure that it was fixed. Now, an awful lot of effort went into this, an awful lot of pain, blood, sweat, and tears, and testing went into making sure that this thing would work. And then ultimately we got to the servicing launch itself, which, just as a tangent here, was a spectacular experience. This was a night launch in Florida. We sat there at Cape Kennedy all night, getting eaten alive by the mosquitoes, waiting for a 4 a.m. launch. And then suddenly it was instant daylight as this thing launched, and was just an absolutely spectacular moment. The team, the WIFPIC-2 team, were actually staying at the same motel on Cocoa Beach where the Apollo families used to stay. And so after the launch, we went to the hotel, and we were all very jubilant, as you might imagine. And we're sitting around the pool with our feet in the pool, drinking champagne. And then we looked up, and in the dawn light, we saw Hubble go over, and then about 30 seconds later, the shuttle following it. And that was it catching up with it. That was spectacular right there. But right after we were done there, we all jumped on a plane and flew to Baltimore, Maryland, by the Space Telescope Science Institute, where we were going to do our orbital verification of the instruments after they had been installed in the servicing mission. And it was part of that process under about 2 feet of snow in Baltimore that very late December morning, where once we had got the instrument in, we started to do what is called phase retrieval to understand the nature of the wavefront that was being delivered and whether it was in fact fixed or still aberrated. And the gentleman that was responsible for all of this, I cannot claim any glory for this at all, was a gentleman by the name of Chris Burrows. He was the one who figured out the fix, the prescription necessary to do this. And I remember I was sitting with him in the control room one morning with a big cup of coffee, and we were figuring out, based on those phase retrieval measurements, exactly what the aberration, the residual aberration was, and how much we were going to have to move the mirror. It was an actuated system that had an encoder in it, and you could move the mirror plus or minus 200 steps to allow us to be able to move the mirror and get the thing right on. And after all of that work, after all of that calibration and worrying about it, the mirror was off by 4 steps. And we looked at each other and just burst out laughing because of all of the angst and tension that had been going through the process. But it was just one of these things where we had planned for the absolute worst and built a sledgehammer to solve a problem that in the end, probably not by any real judgment, but more by luck, came out to be something that we didn't need the full capacity of the system we had built. But it was there nonetheless. If we had gone up there and it had been way out of whack, the system would have allowed us to put it where it needed to be. But it was just a somewhat ironic measure when we finally got there.
That's absolutely incredible. Yeah, the lucky thing with the Phoenix launch is that it was in the winter, so we didn't have to deal with the mosquitoes, and that was nice.
Yes.
Thank you again so much for doing this with me. This has been really amazing, and I really appreciate it.
Well, I hope it gave you the material you needed for the points you were trying to make. So I hope it was helpful.
Oh, absolutely. No, I think I got everything and more. So.
And that concludes episode 1 of The Art of Space Engineering. Thank you all so much for listening in. I would like to give a special shout out to my wonderful friends Addie Cooler and Vivek Chaco for all of their feedback on this podcast and their advice in editing, as I am completely new to this. Thank you for teaching me your ways, oh wise ones. And a huge thanks again goes to Dr. Scowen for lending me his time and for adding some British flair to this podcast. Now, if you like this and you want to support the podcast, follow us on Spotify, Apple Podcasts, or wherever else you may be listening to this. You can can also like this on Facebook, and I'll be posting there about upcoming episodes. If you have the time, please leave a rating and/or review. Any feedback is greatly appreciated, as I really want to be able to structure this podcast in a way that is most helpful to you as a listener. Finally, please share this with your friends too, so that this knowledge can reach anyone who may appreciate it. In terms of new content, new episodes will be published every 3 weeks, and if the schedule deviates from that, then I'll post updates along the way. So here's looking forward to future adventures and the lessons learned from them. Cheers.